Good morning, everyone. So this is the fourth. Oh my goodness, I can't believe we've done four of them. This will be the fourth training session that goes along with the HPC in the City Cloud Cluster training. Now, today, as of today, you have 14 days until the actual event starts. Can you believe that? I know, right? It's coming up quick. Now, today we're going to be focused on CloudyCluster training, which is one of the tools that's being made available by one of our primary sponsors, Omnibon. Boyd Wilson will actually be walking us through an example of that today. So our agenda today, we're going to do a few introductions as we always do, make sure that everyone's aware of our hackathon objectives, the deliverables and resources, a little bit of general information, and then we'll jump into the training. So these first couple bullet points here, we're going to roll through them in about 5 minutes, and then the rest of the time will be Boyd's. So I want to let you know who the organizers are, and a few of them are here. We have Alex Nolt. He's actually over in Estonia right now, so his time difference is a little bit different for us. Amy Cannon, who is here. Amy, you want to say hi?
Hello, good morning.
Good morning. And then we have Dr. Linda Hayden, which I haven't seen her sign on yet. We have Boyd Wilson, which go ahead and wave, Boyd, because you're going to be talking here in a moment. There he is. And then myself, the one speaking, is Jamie Powell or Jamie. And between the five of us, we will be assisting you all through this event. There is one other person I do want to mention that's here on the call, Mr. Josh Kissel. He's actually one of our web administrators extraordinaire. So in other words, we work him to death and pay him peanuts. Wait. We've cut back on the peanuts, right? I just want to make sure. All right. Okay. So we're giving him air. So moving forward, the objective of HPC in the city. This hackathon aims to really utilize the resources, skills, and knowledge that come with the supercomputing conference. It's one of the largest computers in the world. Now, under normal circumstances, we would actually be doing this in person in Atlanta or in the host city. In this case, it would have been Atlanta, but of course, due to COVID, we're making this virtual. But we're still going to keep the theme of the hackathon focused on issues that can affect Atlanta, Atlanteans, or even Georgia. And of course, as you tune your projects, your mentors will assist you with that. You as a participant will develop an understanding about different technologies that we use, as well as application of data analysis, presentation, and or management. And you should also expect to be a little bit familiar when you come out with data science in the cloud. So Google Cloud, CloudyCluster, using collaborative development software platforms, as well as develop some professional communication skills, which may come in handy because you'll be directly interacting with some of our vendors. As far as in the deliverables, now this is the part that you may want to take a note of. For those of you that like to do screen captures on your notes, this is just one of the screens that you may want to capture. At the end of the hackathon, so we start on Thursday and we end on Monday with final presentations at 6 o'clock. At that time, you should have the following. You should have source code, if you've coded something with comments, a PDF of your presentation that includes your team members with pictures, including your mentor, how you use the HPC technology or in your project, as well as how regionally your project can impact, in this case, Atlanta, along with an explanation of your project. All of these things should exist inside of a GitHub repository. So that link you should give to us, and you should pretty up your readme.md file. Our initial training has some information on that. So feel free to take a look at hackhpc.org under hackhpc.org/HPC, and you'll have full access to the slides and videos that went along with that presentation, as well as all the previous training presentations we have. As far as resources for you, the participants, you're going to have mentors and or specialists that'll be with you. You have our Slack channel, which most of you should be a part of. If not, please send me an email and we'll make sure we'll get you part of that. So that will be one of our primary communication platforms. Google Cloud, which you're going to see a little bit of it today. You're going to have provided credits. CloudyCluster, which of course Boyd is going to go over today. And just to let you know, some of the most commonly used skills or built skills during these hackathons are related to Python coding, Jupyter Notebooks, Node.js, which is JavaScript, HTML. And of course, we also have data sets for you, and you've seen those in the emails. But if you haven't, you go to hackhpc.org, participate. You have a link there called data sets if you want to start getting familiar with that. Having said that, now we're actually going to turn our presentation over to Mr. Boyd Wilson. Now, Boyd, I've known Boyd for a number of years now. He has worked very closely with every single hackathon I've ever had the pleasure of being a part of. He's a part of Omnibond. He has a big heart, and he has been a mentor in every hackathon that I've been a part of as well. So without taking too much of his thunder, I'll hand it over to Mr. Boyd Wilson. Now, Boyd, I do have a question for you.
Yeah.
I am going to stop my share, and then that way you have full control over the screen.
Here we go. Everyone see everything okay?
Yes.
Hear me okay? Hope the bandwidth hogs don't take over or whatever. Yes, I'm very excited. Every year, this is one of the high points to do, is to work with the hackathon and just help people learn and understand and be a part of this community. And I really appreciate Jamie and Linda and Amy and Rich and everybody's help, and Josh and I'm probably Alex, and I'm probably missing a bunch of people, but everybody who's helping and has helped and will help, and it's awesome. So what I wanted to do here today is talk a little bit first about just kind of HPC and HTC, because this might be your first interaction with that. And this is associated with the supercomputing conference. And so we should talk about it and think of ways to use it as part of our hacks. But sometimes HPC, HTC is a heavy lift. So, you know, anyway, so let's go over it and kind of just talk about it and give some background. What's interesting, I made this slide and then I thought about the introduction later, but, you know, high star computing. And the reason I say that is when you know, it's at the supercomputing conference, and supercomputing and high performance computing are probably synonyms in the generic sense. You know, it's most generally refers to the practice of aggregating computing power in a way that delivers much higher performance than one can get out of a typical desktop computer. A lot of scientists over the years sit and they do some simulations or they do some models, and then they kind of decide, and they put a sign on their computer in their lab and they say, do not touch for 2 weeks. Please don't let the power go out because this thing is going to run. And then some very smart people a very long time ago came up and said, well, why don't you break that up into multiple places so you can run it all at once? And that's kind of that supercomputing concept. Let's take a data set. Let's take, you know, if you're doing geographic surveys of maps, break up the map, break up your workload a little bit so your code can work all at once. So that's kind of the generic term. And then as things evolved, there kind of came some sub-terms out of it. And there's high throughput computing, or things that are, you know, pleasingly parallel or embarrassingly parallel. I like pleasingly better because sometimes it's just easier. And those are things where, let's say you're just breaking up a data set. And each one can run through its data set. You know, if you want to process some videos, you can break up the video into multiple pieces and then do some computer vision AI stuff on it. And it kind of is there and it's fine. And one of those interactions doesn't have to, you know, worry about what the other one's doing. If the other one dies, it can restart. It just, and that's kind of called high throughput computing. And I kind of call it a subset of supercomputing and almost like a subset of HPC, the generic, which is kind of confusing because then we're going to get to HPC. Sometimes people use the term as the specific, and there's other things you can do. So like if you're doing weather modeling and you need to find out some stuff over in this process, it kind of broke up the problem still into multiple compute nodes. But something over here is dependent on something that is going to happen in a second. They haven't calculated it yet, and then they say, "Hey, tell me about this," and then it says, "Oh yeah." So you have multiple nodes interacting and talking to each other during this HPC job, and those are usually using MPI, which is the message passing interface, and MPI-IO to disk, and so you could do these things and interact, and things can be dependent on each other. You go through, run some stuff here, communicate it to something else, and it can continue on its way. And so it's not, and it's more dependent on those communication paths and other things like that. So I kind of wanted to give that. It's a little confusing, but sometimes when someone says HPC, they mean the generic term, and other times they mean the specific MPI tightly coupled, and they'll differentiate it with HTC. And then again, it's all supercomputing. The title of this slide probably should have been supercomputing. But it really makes things work faster. It's how we can do climate simulations. It's how you could take 100 years of climate simulations, and figure out what's going on, or try to predict and understand what's going on. And so that's where we get this term. And that's what this whole conference is about. And all the vendors are trying to help people accomplish these tasks, and people are really trying to help, make the world a better place through modeling, simulation, even some different parameter sweeps of artificial intelligence, neural net trainings and things like that can even take part in these types of things. And architecture, and this will both be kind of the architecture of an HPC system that you'll see, and this is also the architecture of CloudyCluster, because CloudyCluster was designed to be very similar to what you find at huge labs like TAC, where, Jamie and the other folks from there, manage and help people use these big systems. And the first thing that you kind of get is generally they're built in a private network. And within that private network, there's usually, possibly a NAT node, or there's a NAT router, or something kind of letting all the things inside access the internet, but not letting the internet come into all the different nodes.
So what you're saying here is you're saying, so basically the private network is kind of like our home network. Is that what you're saying? And that NAT is more like our router that allows us to then get out to the public internet, the big internet.
Yeah, the wild internet. And so there's ways that you can get into it, and they're usually the login node. And I don't know if you've ever heard the term bastion host, but it's login nodes probably existed before the term bastion host. It was kind of ironic, but it's really an entry point into a private network as a bastion host. And a login instance is really your entry point into this HPC environment. And that's where you log into, you interact with, and you do things like submit jobs, which I'll get to what those are in a minute, and other things. And then additionally inside this environment, you have something called a scheduler node. And a scheduler node is something where it takes what's called a job script, where you say, okay, I want to break up the problem this way, and I'm going to do it in a shell script, and I'm going to tell all these different things to run on these different compute nodes. That's all done in a job script. And the scheduler's job in an on-premise system is to say, okay, I got a few tens of thousands of nodes sitting out here. Who can use what, and they need how many, and it's really kind of managing that resource so everybody can get through and use it optimally. Sometimes you have to wait a little bit because you're asking for a lot, or there's somebody using a lot in front of you, and that's called the queue, and schedulers have queues. And so you kind of wait in line, and then you get to do your stuff.
So can I ask a question here? I'm trying to make sure I understand this myself. So the way I kind of look at this, so if the if we looked at this as a physical thing, so if we looked at this like a house, and it's a house that needs to be cleaned, so the login node would kind of be like our parents, like our mom. You know, mom sees the house and the house needs to be clean. She'll go to you as the scheduler, the person that's going to make this happen. And she might hand you a post-it note that says that this job I want you to get done. And it says vacuum, clean, wash dishes, paint the house, build a garage, you know, general normal things you do on a Saturday. Now, you by yourself, thinking about the way you would do it now on your individual computer, your one node, you would just have to do each job at a time. You got to wash the dishes, you got to paint, you got to, you know, go to Home Depot to get wood for the garage, but you have to do all those things individually. But if you have little brothers and little sisters and little cousins that are with you, you can then give out those jobs to try to do it in parallel, to distribute it out. So you, the scheduler, may say, all right, cousin number one, because I like you, you just have to do the dishes. Cousin number two, because I like you, you might have to vacuum. Brother number three, remember when you went in my room last week? Yeah, you're on garage building duty. And so that is that kind of how this works.
Yeah, that's a very good analogy. That's excellent. Yeah, and you know, the scheduler's job is to give out the work. And what's interesting is, you know, the scheduler is really saying, okay, here's all the jobs that need to happen. Now, if we kind of take Jamie's analogy and we take a little bit further, what if, you know, the garage building is one job? There might be, maybe there's two or three cousins helping with the job building because they were a co-conspirator with brother. And then that whole job is going to be done by multiple processes too. So you're breaking up the work across jobs, and then you're also within a job, you're breaking up the work. It's not a single computer, it's multiple computers. So it's a very good analogy. Um, Another interesting thing that you'll see is, and that's the compute. So if you think about the scheduler, it's going to say, okay, this job needs 4 compute nodes, this job needs 100 compute nodes, push them out there. In a HPC environment that's on premise, those compute nodes will be sitting there waiting. They may have done a little bit of imaging, configuring, or doing some things before you're ready, but they're sitting there and running. The difference in the cloud, and what CloudyCluster helps with, is those nodes will actually dynamically spin up because you only want to pay for the things while you're using them. And then the job will run, and then when it's all done, it'll actually tear down those nodes. Whereas on an on-prem system, they would run, when you're done, it would just move on to the next system, or the next job, sorry. And then there's also some parallel storage, where if you want to put stuff so your different nodes have access to the data, your different compute nodes, when they're up and running and doing their thing, they got to have their data. So if you put the data on the parallel storage, the reason it's called parallel storage is it breaks up the file system. It's kind of like your local hard drive, but it breaks it up across multiple computers so it can get more throughput, be a little faster, and support more things beating on it. And then once, you know, then you put the data there, the job launches, it accesses the data on all the nodes that need it. If it's an HTC job, each job will probably have been configured to look at a different section of data and just process it faster that way. If it's, you know, an MPI job, or a, you know, a lower level HPC job, not the generic term, then you will get, you know, they might look at the same set and do different things and then communicate, or they still might break it up, but they're going to be interacting. Those compute nodes are going to be interacting with each other within that job. It's kind of like if someone's holding up one end of a ladder on a garage and someone's handing someone a shovel, but someone else is using the shovel, you know, say, hey, give me that shovel or hammer. Hammer probably makes more sense. Wait, I'm using it. Okay, now you can have the hammer. Or here, read the plans, tell me what I need to do here. So there's going to be more interaction, as opposed to, you know, someone dividing up the room and saying, here, you scrub this part of the floor, which would be more of an HTC job. There's also some things like object storage and cloud storage, which you can use to get stuff in and out. But that's really the components of an HPC system. And then there's a lot of software that help you do things on those compute nodes as well. So the HPC Job, and I was scrolling through Netflix and saw the Italian Job as a movie. I honestly think it's a bank heist or something. It's been a long time since I've seen it, but trying to be funny. The Job, the HPC, not the Italian. Those are shell scripts. And here's an example of a shell script. And what's interesting is you see all those hashtags in front of things. And those aren't Twitter things, those are just comments. And what's interesting with the job scheduler is it actually goes through and it says, oh, if this thing only has one hashtag, it might be relevant to me if it has a keyword that I care about. And since we're using, say, a Slurm scheduler, then SBatch would be the one we care about. So you kind of see in the middle here, I can't highlight in presentation mode.
So for those of you that may not be familiar with bash scripts and things like that, and shell scripts, you can look at this as being that post-it note that the mom gave you, that your mom gave you to do the work. So in this case, it's telling you to make sure you can use the program OpenMPI, and then make sure you can get to this particular space on the hard drive so that then you can run this actual application. So it looks, at first look, it looks a little bit overwhelming, but as you start to break it down, and keep in mind, you will have mentors there to assist you as well, this starts to make a little bit more sense as you use it.
Yes. Yeah. And a lot of it is boilerplate. So it's like SBatch, and that's the number of nodes. I want to do this job over 4 nodes. And then here's the number of tasks per node. So that means, the number of processes that you can run, usually number of cores that you have on a system. You can use this command to say, okay, I'm going to spawn this many tasks. And then when you get down to and that also determines which node you're going to use. So in the cloud, it'll actually spin up something that has 2 vCPUs, which are kind of hyper threads. You have to kind of think about that, but we'll help you if you run into anything with that. Then there's also, the other concept, if on an on-premise system, people would probably grump at you only using 2 tasks per node because you want to use those nodes more efficiently because they generally have more nodes. And generally when you're doing HPC things, you'll spin up something a little bigger than this. But that's a good example. If you notice, there's some things called, export, and there's module add, and module add is a thing that say I just want to use OpenMPI versus MPitch, and those are different MPI libraries. I grabbed an MPI example here, and then if you notice, because it's a very simple MPI prime job, that's some code that's out there that you can compile very easily, and it's something that we kind of use as a sample inside a CloudyCluster people to make sure things are working right. And then at the bottom, you'll see that MPI run, and then the number of processes, and then it goes off and does the MPI prime, and it breaks up the work and gives you the total number of primes based on the configuration that you set up. But that's just an example, and I just wanted to focus more on the script, the sizing of things. And if you notice up at the top, there's this hashtag CC. There are some specific CloudyCluster hints that you can use. You don't have to. CCQ, which is that meta scheduler that kind of spins things up and then hands it off to Torque or Slurm or the scheduler, and then tears things down when they're done, can kind of understand the standard SBatch and PBS commands. And we'll focus on the SBatch ones for this hackathon, just because most people are more familiar with or use it more day to day. But that GCP UP, that means use preemptible, and GCP, which is just a type of instance that you can do. You can also say, oh, I want to make sure I'm using this type of instance because I want this. Or if I want a GPU node, those are the kind of things where you can control that. And if you go to docs.gcp.cloudycluster.com, then we can help you with that. There's all kinds of things that you can put in there, but that's where you can control what kind of node spins up in the cloud. So it's kind of an overview of a job script. There's mentors to help. Don't let it be overwhelming. It's not. Here's an example, just kind of, because sometimes it takes a while for jobs to run and we don't want to watch paint dry. And so here is, there's a CC, so you'll type CCQ sub, and I noticed my screenshot here doesn't even show, but if you type CCQ sub, and then the name of the job script, which is MPI prime, and 2-8 means 2 nodes, 8 processes per node, just my nomenclature I use for things when I'm testing stuff. And then you'll notice there aren't any compute nodes. So then it launches, and if you notice, you can also type CCQ stat after you type it. So up there's a CCQ sub up there higher. That's what I did. CCQ sub MPI prime 2-8. It's like up here, and get your magnifying glass out, but trust me, it says that. And then down here, what we typed is a CCQ stat, and that actually just lists the jobs for you. It tells you what stage they're in, what's happening, and what's going on. There's a CCQ stat command in its full entirety. And you'll notice at this point, there's 3 jobs nearly running, and then there's compute nodes, a bunch of compute nodes that are spun up. And then once they've all completed, and a couple of minutes for things to finally tear down, all the nodes are cleaned up, and you just have that base environment, login node scheduler, and parallel file system. So this is what the interface will look like for when you're interacting with CloudyCluster. And again, this year we're going to have projects set up. We'll have for each team, and then we will have a CloudyCluster environment already set up and running. So you don't have to go and set it up like we've done in previous ones. That took too long. We're trying to get the data done. Setting it up isn't hard. It just takes 20 minutes for all the things to spin up, connect, auto configure, and do that. And we don't need to do that. So we have the ability to pause and resume, so they'll be paused. And that way you can get in and use it for whatever aspects you want much more easily. So let's do some live stuff. And how much time do we have? Got a half hour. We probably won't take the whole time. So since we're going to spin these up, this is what CloudyCluster looked like when it's all spun up. If you go to the main screen, you'll get this. You'll be prompted to log in. It's a login page. I'm not going to log out and log in and show you that. We've all seen those. And this actually goes in interrogating. So right now, here's our login node, a representation. There we have Slurm scheduler. There's actually a GCS bucket. And then there's this control node, which I'm talking to. And if you notice, each one of these has Cheetah, Jade, Angler. We actually take 3 names and automatically concatenate them. And that's how we do the DNS names. And then we set up SSLs or TLS so everybody can be happy and secure. But that all happens behind the scenes. And so one way to get into this is click on the node and say, hey, I want to terminal in. And then you can just say void and the password I set up. And then we have a shell into the system. There it is. We are in the void directory. If I do cd / sample jobs, MPI, GCP. And if we look, there's that MPI prime.sh. And so you can see you can interact. It's the login node, and you can do things. And I can actually submit a job. If I could type right. And so now that same job that we kind of showed, and I've messed up something. That's okay. This is what I do normally. I forgot to comment. I must have edited another job script. So actually, the reason I didn't know what to do is because there was nothing uncommented. So now we're going to say, okay, I want 2 nodes, 2 tasks per nodes. And then we're going to do the MPI run, and we're going to do -np number of processes 4. And then it's going to run that MPI prime code. I'm hoping we'll make sure it's compiled. So if you notice in here, there's an MPI prime compile, and it's just compiles the source. That's all it does. I'll just run it. Okay, it's compiled. And now we'll do another CCQ sub and see if it's a little happier. And now we have an X. Yeah, this is, it still didn't like my scheduler. Did I? Well, interesting. We'll move to another environment. I've been testing some things. So let me show you what I've been testing. And I think I'm using some brand new code. But if we go over here to one of the things that we've been testing and trying to get in place for the hackathon is what I've probably messed up everything is actually getting Jupyter Notebook up and running on top of this, on top of CloudyCluster. So it automatically comes up with CloudyCluster. So right here, we see we have Jupyter Notebook running on top of CloudyCluster. And so what's really interesting here is Jupyter Notebook, open on demand, gives us the ability to have interactive Jupyter Notebook and interactive sessions to compute nodes. And what we can do here is do some very interesting things. So we can look at your home directory. You can look at the active jobs running, which here's the active jobs running. And then we can actually go and start an interactive Jupyter Lab session. So we want to run this, launch it for an hour. And this will actually give you, this is the wrong version. This is what I've done. I've got my two versions confused. Aha. When you try to fix something and you work in the wrong window, you end up showing everybody really bad stuff. So you won't see any of that. So
I will tell everyone that I'm sure, of course, Boyd goes through this, and Josh and Dr. Hayden and just about all of us. Whatever is the worst thing that Murphy can throw at you it will happen during a demo. You will practice it and make sure everything is ironed out and working well, and then you demo.
So this is a lesson for your presentations at the end. Any windows that have broken stuff in it, you close them before your demo. So here's an interactive Jupyter Lab session, not in some window I'm trying to do something weird in. So here's the interactive Jupyter sessions. And so you can connect to Jupyter, you can actually connect to, and I launched these jobs earlier, so you didn't have to wait 3 minutes. So here's an interactive VNC session, no VNC session, to a compute node that's running for a set amount of time. And then we can actually interact and see what's going on. If you notice, you can still see the shared file system under there. There's other people that have played with that and set things up on this environment. And so this is what I was wanting to show in the other window. And also you have the ability to have Jupyter Lab running on a compute node, so you can do some interesting things. And also, if you saw that first shell, we actually get the ability to have a little bit nicer web shell into it if you want. And so you can interact and do those types of things. So this is, what I wanted to show. So in addition to that, we'll go back to the broken one because it's entertaining. And you'll see this environment. You also have the ability to go to a dashboard, see jobs that are running and those types of things. And then also the access tab. And the access tab is, here's how to access open on demand. And this is something we're working on real time because we thought that would be easier for people to use and interact with. You also have WebDAV access, you have other things. So you can easily get access to the different nodes. You can, do terminal into the sessions. And if a compute node is up and running, you can actually SSH into that compute node to see what's going on. And so you have this environment that's ready. And I do apologize that I was playing in this one and not the other one. But you get the idea. You saw the sample, you run the jobs, they'll run. You won't see those weird things that I was trying to make
Boyd,
Jupyter.
I was muted, and so you didn't hear that. But I did want to make sure that they saw that visual HPC selection.
Yeah,
That one actually, there, I have seen several teams kind of get caught up on this. So, as a system administrator, I am very comfortable sitting at a blinking cursor because that's where I live. But most people are that way. They like to have a desktop where they can click on items and things like that. That setting right there. So under access, under visual HPC, where it says persistent VNC for all environment, enable my persistent VNC. That's what allows you to actually go to the desktop of the computer. And so of course the item is there, but so just to highlight that, let's see if I can use my magical teaching skills. That setting right there is extremely important. So, all right.
right.
Thanks, Boyd.
Yeah. We'll see if this works in this broken one I've been playing with.
Uh-oh, he's going to go off demo.
I'm going, well, we went off demo when I went to the wrong set of tabs anyway. It was all off demo. Anyway.
If you want to use that though, talk to your mentor.
Yeah.
Because not all VNC clients work.
Right.
Yeah.
And so by clients, we mean there's software packages that allow you to have that visual desktop. So you can look at this as being something like a remote desktop. TeamSpeak used to have it back in the day. And of course, my desktop at home. But anyway, that's what that's for. And like I said, we can assist you with that. So you don't have to always stare at that blinking cursor if you don't want to.
Right. And that's part of why we're working on integrating this Jupyter Lab integration. And you see we get to this. Now, the one thing that Jamie pointed out that's very good is this is a VNC session into a compute node that has a time limit, and eventually it will go away. Now, you can store stuff on the shared disk and everybody can use it. That's my timeout for the other thing. And so you can use this, but the one that Jamie showed was actually, to the login node. And that one stays persistent and stays up, and you can see what's going on, and it kind of persists. And if you pause and resume, the data on those local nodes will stay there. One of the things in the cloud is there's ephemeral nodes and there's kind of more persistent nodes. And the compute nodes were all thought of more ephemeral. So they kind of spin up and tear down, and all the stuff locally on that node disappears. That's why you want to store it on a shared file system, or you want to copy it local. It won't be there. But on the login node or the scheduler node, the stuff stays there. So you put stuff there, do stuff there, it'll stay there. So that gives you kind of a difference of how to do those things. And then the next piece I would like to show is just a kind of a teaser into Jupyter. So there's something called CCQ client that could be helpful. I gotta move this menu thing, excuse me. Here we go. And I'm not gonna spend too much time on this, but if you notice, there's an import CCQ client. Now this is actually code from a previous hackathon that I'm kind of working on and cleaning up and hoping we can make available and get working in the next week or so. I just pulled it up yesterday and started looking at it. But what this Jupyter notebook will do will actually allow you to create HPC jobs and actually submit them from anywhere. And what it's using is the CCQ client. And since I can't find that window, we'll just go to GitHub or go to the CCQ client. This is a public repo. And you'll see in here the CCQ client, and you actually have to install it into your Python. That's why it's called that underscore weird thing. It actually renames to CCQ client. If you don't want to install it, you can actually just rename it to CCQ client, put it in the same directory as where you're calling it from. And it imports a few things. So there's other things that need to be on there. We'll make sure the image that we spin up for everybody has those things on it. But if you want to access it locally, if you want to just use Jupyter Lab locally and interact with it like I was doing in that other window, you'll get down to here, but there's just these simple commands: CCQ sub, CCQ stat, CCQ delete. And if you'll notice, you'll just pass kind of some of those parameters that you saw in a job script. And then we'll have some simple examples. And that's why I wanted to work on that Jupyter notebook. So this way you can actually, in your Jupyter notebook, say, okay, launch these 3 jobs to calculate this data and save it back to scratch. So then we can look at it and review it. So it gives you a way to interact with those HPC environments without having to do everything from the command line. So this is available to everybody. And again, down at the bottom are the commands you want to call. They're just wrappers for the others. Go ahead, Jamie.
So let me give you an example of why you might want to do this. Let's say you have a very large data set. Now, I'm going to caveat this because I know a couple of the mentors are going to scrunch their nose the minute I say this. So caveat it. You're not going to be able to make this perfect, but this is something that you can do at least begin the process. Some of you all may want to use machine learning to explore some of your data sets, to build a model of your data set. And in order to do that, you have to run it over and over and over and over again. Well, some of you may want to use scikit-learn or something like that that you've learned in class or that you're aware of to do that. Or TensorFlow. Some of you all may actually want to use TensorFlow. I'm not saying you're going to get a perfect model. I see your face, Rich. I'm caveating it hard. But this is a way you could do that programmatically and visually inside of a Jupyter notebook that fires off that job, starts that TensorFlow job so they can run and then produce the results. So that's one way you may want to do this. There are many others, but just to throw something out there to kind of put it in your mind.
Yes. And so there's lots of things that you can do and where you need to divide up that data. And one of the steps that I want to talk about is when you're going through thinking about how to work on your problem, it's better to work on the simple version, get the code working, and then try to do things in parallel. Especially if it's your first time through. And that's why you'll think of more of, okay, how can I divide up this problem to do it faster? And you may not have something that takes 4 weeks to run. You know what I mean? You might have something that takes an hour for run and you want to show you can break it up and run it across 3 or 4 nodes and run it in 15 minutes or 20 minutes across all 4 of those nodes. Then you're understanding the problem you're trying to solve and you're understanding how HPC can help. And that's what the supercomputing conference is all about. That's why these things are here and these tools are available to help you understand those problems. So when you get into other problems, other areas, other data, you understand those tools and techniques. And what we're doing at the hackathon is teaching and helping people learn and understand hands-on these techniques. Anyway, let's go to any questions or thoughts. And
there we go. Hey, Boyd, would you mind throwing up the general information, the slide right before the, yes. There we go. So Boyd, first of all, I want to make sure I say thank you. Again, Boyd, as you can tell, is a wealth of knowledge, and it's no secret that CloudyCluster is his baby. He can make it dance. So, and he will be there, even though he's going to have his own group as a mentor. As students, I never call the hackathon a competition. I always call it, I always call it a hackathon because it gives, because we act as a family inside of the hackathon. We're there to help each other. So if your team needs assistance with CloudyCluster, we can grab Boyd and say, hey, Boyd, we need to borrow you for 10 minutes. Or hey, Rich, or hey, Josh, or hey, Mary. And
Yes.
we can do that. So I don't want you to think that just because Boyd has a team that he is not there to assist you. And if you have an idea and you think that using those resources is what you need, talk with us about it. We're here to help you. Now, having said that, there's something I'll always give during these presentations or during these training sessions, and that's the 3 T's. So this is just a quick reminder. So each of the teams will have 4 to 5 students. We recommend 4. 4 we found is that optimal number. There'll be 1 primary mentor and then 1 specialist to assist that member on each team. The times will be, well, of course, we're starting November 5th at 6:00 p.m. That's when we're going to form our teams, and the mentors are going to come out and try to seduce you with their amazing projects, as well as some of the students actually have projects that they want to create. And then we'll have check-ins daily, that Friday the 6th, Saturday and Sunday at 11 a.m. Eastern and 6 p.m. Eastern. And then final presentations will be on that Monday, the 9th at 6 p.m. Some topic examples you may want to get into your mind and start thinking about. We've had examples of COVID-19 analysis, not just COVID itself, but the processes and logistics around it. We actually have a mentor that is a health professional that has a project where she has to schedule nurses over 12 different hospitals and trying to see where they go and things like that. So it doesn't have to be exactly a thing. It may be another problem that you're taking a look at. Economic disparities, genomics, molecular, weather modeling, social justice, presidential elections. So one more thing I always like to throw out there. So our hackathon starts November 5th. It may be an interesting time after November 3rd, just saying. Public data management, graduation rates, broadband access, insurance and public health. All these things are topics that you maybe want to consider. And next week, we will be actually releasing some of the projects that the mentors have already informed us they would like to be working on. So having said that, if there are any, oh, that's right, Boyd is controlling it. Boyd, would you put in the next slide there? I'm like, Boyd, won't this slide move?
Let me put in 2 more things. If we're going to be setting up this project, because I forgot, sorry, and
No problem.
sorry to mess up your flow.
No, not a problem at
all. We will be setting up CloudyCluster environments, and someone else will test them and make sure they work, and you're not getting Boyd messing with code stuff. And what we're going to do is, if people want to play with that beforehand, we're actually getting the credits in a couple of days. Mm-hmm. If mentors would like to play with those environments, reach out to Rich, myself, Josh, Amy, and we'll give you access to some before the hackathon so you can be familiar with it, see what software is there. And then if you have questions on those types of things, we don't want to hold that up during the hackathon. Then we will have those set up for you. So if you want to play with it ahead of time, just reach out. And that includes some of the hackies or hackers and the mentors. And so we can set that up, and we can spend a little time with you showing it, so that's something we're available over the next 2 weeks to do. And we don't think that's giving anyone an advantage because it's open to anyone. So please reach out if you need that. And we'll probably have these set up early next week to mid next week is our goal. And then we can let people play with it. So sorry to interrupt.
No, that's not a problem at all.
The fact that you are in attendance gives you a bit of an advantage. So good job showing up.
Yes. If you wouldn't mind going to that last slide there, Boyd.
I can do that.
Thank you. So there's Boyd's information. These slides will be available online at hpc.org/HPC here shortly. So as soon as this video comes down, it needs to download. I edit it a little bit, slap it up on YouTube, and boo bam, it's ready for you and your friends to enjoy to your heart's content. You might want to get popcorn. So, but having said that, again, we're here for you. If you have any questions, please let us know. At this point, I'm going to go ahead and stop the recording. But thank you for joining us. And we have one more training session waiting for you next week. And it's going to be an interesting one. Having said that, take care.